All right, we've talked about exponential functions and money. And often when we're investing money, the interest rate is compounded, the interest is added on a limited number of times a year. Monthly, 12 times a year, quarterly, only 4 times a year, or maybe even daily, 365 times a year. But many things that grow exponentially actually compound continuously. It's not just a limited number of times, but it's continually compounding and growing. And so whenever we have this continuous exponential growth, we have a different formula that we're going to use for these scenarios. Continuous exponential growth. The formula that we're going to use is y is equal to c times e to the kt power. It's a little bit simpler than our other formula. And let me tell you what all these variables stand for. The y variable, this again stands for the resulting amount, how much we end up with. The c, just like the p in the previous formula, is the initial amount. E is just the base of the natural log. E is the number 2.71828. So it's just a number. K represents the rate of growth. And T, of course, is time. Now, when we're dealing with money, time is almost always measured in years. But when we deal with other types of things that grow exponentially, our time could be measured in days, it could be months, it could be years. It really could be any unit of time. So if you have your handout for exponential growth and decay, let's look at the first question together. Question number 1 says that at any time t, the number of bacteria present, y, is given by this formula. Y is equal to c times e to the kt. So that's the formula that I just gave you. The initial population is 1,000, and the population triples during the first 5 days. And they want us to write an expression for y at any time t. So I've got a little bit of information about this bacteria population. We're starting out with 1,000, and it's tripling in 5 days. The thing that I don't know is that growth rate, and that's a piece of information that we need to find. So I'm going to start out, I'm going to go ahead and rewrite the formula here. Y is equal to c times e to the kt. So I know that my initial amount is 1,000 times e. The k I do not know, but we need to find it out. And the time is 5 days. And after 5 days, my population is going to triple. So that means I'm going to end up with 3,000 bacteria. So I need to solve for I need to solve for k. Now notice k is in an exponent, and so that means we're going to have to use a log at some point to undo this exponential, but I need to get that exponential term by itself, which means I need to cancel the 1,000. Since it's being multiplied, I'm going to divide, and so I get 3 is equal to e to the 5k power. Now I have the exponential by itself, and I'm ready to use a log. Since my base is e, we are going to use the natural log. So I'm going to natural log both sides of this equation. The natural log and e cancel out, and I have 5k is equal to the natural log of 3. And then the final step, I'm going to divide by 5 to solve for k. And if you put that in your calculator, natural log of 3 divided by 5, we get a k equal to 0.2197. So now we're ready to write an equation that we could use to find the number of bacteria at any time. I'm going to go back to our original formula, and we're going to say that the number of bacteria in any time, y, is equal to the initial amount, which is 1,000, times e, Our K, we just figured out, is 0.2197, and then I can multiply that times any time t. And so that's our equation, the equation that they're asking for in part A of that question. Now question B says, by what factor will the population have increased in the first 10 days? So they're giving us a new time, a time of 10 days, and so I'm just going to substitute that into the formula that I just created. 1000 e to the 0.2197 times 10. And if you put that in your calculator, you get a resulting population of 8,997.979 bacteria. Now the question said, by what factor does it increase? Our factor of increase here is 9. We have 9 times as many bacteria after 10 days as we had when we started. The factor of increase is 9. And then our final question here, question C, at what time will the population have increased by a factor of 6? So for question 6, we want the resulting number of bacteria, for question C, we want the resulting number of bacteria to be 6 times the original amount, which means I want to end up with 6,000 bacteria. I'm still starting with 1,000 bacteria. My K is still 0.2197. Once you find K in these problems, it's never going to change. And then times T. So again, I'm looking at a variable in the exponent, which means I'm going to need to use a log to solve this equation. First step, I'm going to divide by 1,000. And so 6 is equal to e to the 0.2197t. And now we're ready to log both sides. Since my base is e, I'm going to use the natural log. And the natural log and e cancel out. And so I have the natural log of 6 is equal to 0.2197t. And final step, to solve for t, we're going to divide by 0.2197. And the time to reach 6,000 bacteria is equal to 8.155 days. Now on all these problems on the exponential growth and decay worksheet, on most of them, you're going to need to initially find what the K growth rate is, and then plug that back into the original formula, and then use that formula to find the other pieces of information that are being asked for.